All right, folks, today we're going to be covering the last type of transformation, and that is a dilation. Okay, when we think of dilation, okay, some of you may have had your eyes dilated at the eye doctor. Okay, it just means they got bigger. Okay, but a dilation really is a stretch or a compression. Okay, so the figure could get bigger, but it also could get smaller. Okay, so it says an enlargement, so it got bigger, or a reduction got smaller of a figure by a specific scale factor. Okay, this is our only transformation where the size of our figure changes. We've been practicing so much looking at our graphs and making sure they were the same size and the same shape. This one, the size actually changes. Okay? What we're going to do first is talk about this scale factor in general. A scale factor we've worked with before, way back in Chapter 7, when we talked about similar figures. Okay, well, when we're talking about looking at our original triangle and our second triangle, if it gets bigger, we say those aren't actually congruent. Okay, they're not the same size. But since they stay the same shape, they are actually similar figures. Okay, if you recall, similar figures have the angle measures all stay the same, and then the sides all change by the same scale factor, and that's what we're focusing on today. So, looking at our picture here, the first thing we want to do is decide whether we're getting bigger or smaller based on moving k to k prime. So we have to look at which one of our pictures is the original, because it won't always be left to right or up and down. Look for the original k. So our original k starts here, and you'll notice that's the smaller one. If our original k is smaller, that means this must be an enlargement because we're making it bigger. The next thing we want to be able to do here is find the scale factor exactly. Now, a scale factor just means we're multiplying by something from the original to the new. Okay, so our formula is going to look something like this. We'll take our original, we'll multiply by our scale factor, and scale factors from Chapter 7, they use k to represent that. They're going to use an r to represent the dilation here. Okay, so make yourself a little note. That is your scale factor today. And then that will give us our new, or our image. Okay. So looking at our picture here, we have an X for our missing information, but from this point, which is our center of dilation, we're only going to do this on the origin, okay, but this center could be technically anywhere. What we'll do is look from that to the point that we start with, and that will be the value we call the original. For us here, that's X, but we can use our diagram to go solve for X pretty quickly. I know the total distance from this point all the way to k prime is 7, but then this distance between k and k prime takes up 5 of it. That means there's 2 left. So the distance from that point to k is 2. That goes in for our original. We're trying to solve for r, so just keep it right there. And then our new, okay, k prime, the whole distance from this point to the k prime was 7. Solving for r, we just have to divide by 2 on both sides. So r equals 7 halves. So we would call this a dilation of 7 halves. Now, what that really means for us, we're used to thinking about numbers more commonly in decimals. If you take 7 divided by 2, it gives you 3.5. That tells us this figure is being stretched by 3.5. Now, the next one, again, we first want to decide, is it getting bigger or getting smaller? So find the original in the picture. Okay, k is right here, so our original is bigger than our new figure, which means this is a reduction. Okay, or we compressed the figure. Now to find our scale factor, we're doing the same thing. We take the original first. So our original this time is our longer distance. Okay, we're going all the way to regular K, and that distance over here in the picture is 5. So 5r equals, then we want our new, okay, so our K prime here, that distance is 2. So then r, we just have to divide by 5 there, is 2/5. Okay. So we didn't even need x in this particular picture, but the distance we know, if we've taken up 2 of the 5 here, there would be 3 left. All right. Now just like with our other transformations, we're going to take a look at what this looks like on a coordinate system. So first step is always graph the original points if they're given, or highlight the original shape if it's already graphed for you. Okay, so step 1 here, we're just graphing these points and highlighting them on our picture. So 2 to the right here, up 4 is our J. Then 4 to the right and 4 up is K. And then 3 to the right and 2 up is P. We'll connect those. Make sure you're using a straight edge on this. Now would be a good time, if you didn't have a straight edge or highlighters out, to grab those before moving on to the rest of this problem. Okay, now that we've done that, if we said a scale factor is just something we're stretching or compressing by, scale factor in our last problems we took and multiplied by. So that's what we're going to do with our ordered pairs as well. They only give us one number, but every single piece in our ordered pair gets multiplied by that same number. So to get to this, all we have to do is take both of these pieces in J and multiply them by 2. Okay, so that looks like 2 times 2 and 4 times 2. 2 times 2 is 4. 4 times 2 is 8. So our J prime is 4, 8. We'll do the same thing with the next one. Okay, we're taking our original 4 and multiplying it by our scale factor, which was 2. Taking our original second value and multiplying it by 2 as well. So 4 times 2 is 8. 8. Last one here, we're taking 3, multiplying it by 2, and 2, multiplying it by 2. 3 times 2 is 6. 2 times 2 is 4 for our final ordered pair. We'll go ahead and plot those on the same picture here. Going 4 to the right and up 8 will give us our new J value, so J prime. Right 8 and up 8 will give us K prime. And then right 6 up 4 will give us P prime. When you're done here, okay, we always want to check that our graph is following all the things it should. We've talked about shape, size, and direction so far. You'll notice that they're the same shape. They're definitely not the same size, but the direction shouldn't change either. P started at the bottom, it stays at the bottom. Okay, so same shape, same direction, but the size changes. Now, just for extra here, since we went with our original was a small one and we got bigger, this would also be an enlargement. The next one here, we're going to take 3 points again and scale them by the factor 1.5. So we're starting out with plotting these points here. -2, 0 is D. 0, 2 is G. 2, -2. is F. Go ahead, connect those 3 points, and highlight it in your first color. This scale factor, since we're dilating through the origin, is going to be applied to both the X and the Y in your ordered pair here. So again, we're taking each piece and multiplying by our 1.5. And let me just go ahead and change this to a little different version of multiplication since we have a decimal. That way you don't, or you aren't confused by that decimal there. So negative 2 times 1.5, okay, type that in your calculator, will give you negative 3. And then 0 times anything is always 0. What that tells us is anything that starts on either your x-axis or your y-axis, okay, it will stay on your x-axis or y-axis, okay, when we go ahead and graph that. The 0 never changes. So the next one, same concept, that 0 won't change when we multiply by 1.5, but the next one, the 2, will. So we'll start out with 0, and then we're taking 2 times 1.5. Well, we already did that to get 3, but this time it'll be positive. Last one here, we're taking 2 times 1.5, and then we take negative 2 times 1.5 to get 3, negative 3. We'll go ahead and plot those. Negative 3, 0 is your D prime. 0, 3 is G prime. And write 3 down 3 is F prime. And we got bigger again, so this is another enlargement. Now I want to take a minute here to just talk about what's a little bit different from the last one to this one. Okay, so back at this picture, since we're dilating from the origin, when we make something bigger, it gets farther away from the origin, okay, because we're really stretching that distance when we're talking about our ordered pairs here. We're going over that 2 and up that 4, so then when we stretch it, we have to go over farther and up farther for our new one. Well, with this one, since we had the origin, we're going all sorts of directions from the origin. Do you see how our original shape, the origin fell in the middle of it? When we enlarge it, that means, okay, we're going to be completely outside of that figure when we stretch it. The same thing goes with the reverse of that. So let's talk about each of these. If we wanted to reduce this, then when we do it by our factor, since the origin started in the middle, we should get closer to the origin, and so our new shape would fall entirely inside of this one. When we're not in the origin, okay, so if this was a reduction, we would get closer to the origin when we shrink that thing. Okay, so enlargement, we're going to get farther away from the origin 0, 0. When we're reducing it or shrinking it, it's going to get closer to the origin. Last one here, I've already graphed it for you, so let's go ahead and highlight that and write our ordered pairs. The first one, we're going to the right 5 and up 4. B, we're still going to the right 5, but now going down 2. C, we're going to the right 2 and down 4. And D, left 1, down 2. We're doing this by a scale factor of 1/2, So every single piece we just have to multiply by 1/2. So first up, we're taking 5 times 1/2, and then 4 times 1/2. So 5 times 1/2, okay, it's just 5 divided by 2, 2.5. Okay, I do want you to write these as the decimals versus the fractions. We can write that as 5 over 2, but when we're graphing these and we have a decimal, that just means the halfway point between 2 and 3. So we want to be able to see that decimal to graph it more easily. The next one, 4 times 1/2, or half of 4, is 2. Next one, we're doing the same thing. 5 gets multiplied by 1/2. Negative 2 gets multiplied by 1/2. We already did half of 5, that's 2.5. Negative 2 times 1/2, negative 1. 2 more points. Pause the video, get those done for me. We're just dividing both by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. Make sure the sign stays. 1 divided by 2 is 1/2, 4.5. 2 divided by 2 is 1. Okay, signs stay the same here. Let's go ahead and graph those new points. 2.5 is just 2, and then halfway through the next one, up 2. Alright, then the next one we're going to look at is 2.5 negative 1. Then 1 negative 2. And negative half, so just go halfway, and then down 1 for d prime. Connecting those. And you'll notice here we got smaller, so this is a reduction. And because we got smaller, that really means we're getting closer to the origin. Okay, our points are all closer by that scale factor of 1/2. Okay, I'll use this first one kind of as an example here. You'll see the distance from A to A prime. Okay, it got cut in half there. All right, that is all with dilations. On the back side, we're actually going to do a little bit of review of everything. Okay, there are 4 types of transformations we learned: reflections, translations, rotations, and dilations. So really quickly here, we're going to review what each of these looks like on a graph. I really encourage you to take notes here somewhere. Okay, just right above size and shape, shape and direction, things like that. Okay, so on a reflection, we had the same size and same shape, okay, but it turned around a little bit. It was a little backwards. A translation was the same size, same shape, and same direction. Okay, we picked that figure up and just moved it right, left, up, and down on the graph. Okay, so size, shape, and orientation stay the same. Rotation, again, same size, same shape, but it was turned around a little bit. And dilation, same shape and orientation, but it was a different or a different size. Okay, looking back at these, they weren't the same size. So dilation is the only one that's a different size, so that should be very obvious for us. Translation is the only one that has the orientation stay the same, so if it starts pointing up, it stays pointing up. The only thing we have to really worry about is the difference between a reflection and a rotation. And what we'll do for this is the check that we did for a rotation, we had 90 degrees, 180 degrees, and then 270 degrees. If when we connect our A to A prime, B to B prime, and C to C prime, they show the same angle, that will tell us it's a rotation. Okay, so we'll look at that more in detail as we go. So our first problem here, number 6, we're going to ask ourselves, are they the same size and shape? Hopefully you'll notice they are the same size and shape. They're both triangles, and they both are the same size in terms of the length. LR is the same length as LR there. Okay. Now we want to see, are they the same direction? Okay, so this R points up, but this R points down. So right now I just eliminated translation. Because it's shifted around, we cannot do that one. So we're stuck between a reflection and a rotation. Here's how I want you to decide between the two. Okay, grab a first point R, and if it's a rotation, if we connect this to the origin and then connect it to R and do that for all the points, they should match up. So on your graph here, since this is not what I'm grading, but your answers is, let's mark this up a little bit. Make a line from R to the origin, and then from that origin to R prime. And just notice the angle there. The angle, if it's a straight line, is 180 degrees. If this is a rotation, all of the other connections should match. So the next one, K to the origin, and the origin to K again, is a line, and that matches up. Last one, L to the origin, and then the origin to L prime. All of those form lines. That makes it a rotation. Specifically, a line is 180 degrees. So this one is a rotation of 180 degrees. Next up, first question, are they the same size and same shape? Okay, again, we've got triangles. The angles look like they're the same here, different direction though. If they're different directions, they can't be a translation. If they're the same size, they can't be a dilation. So again, we're stuck between a reflection and a rotation. How would we decide between the two is just what we did last time. We're going to connect our points to the origin. So with your pencil again, let's line this up. L to the origin to L prime forms, you'll notice, a right angle. We have to make sure all of the other connections do the same thing. Okay? Testing one is not good enough. You have to test them all. So then V to V prime, that's also a right angle. So far so good. And then Z to Z prime, also a right angle. So we are forming a right angle, but hopefully you remember that a right angle could show up for a 90-degree rotation, but it also could show up for a 270-degree rotation. We have to decide, is this going just 90 degrees or is it going all the way around? Okay, so let's just focus on L to L prime here. We always start with the regular letter. Okay, so regular letter going counterclockwise, because that's always the way we measure angles. Does it go 90 or does it go all the way back around? Okay, in this one you'll see it goes exactly 90 going that direction. If these were switched, just to show you, if they were switched, it's still a right angle there, but we always start at the original and we always go to the left after that. So this one, we'd have to go all the way to 70 to get to the prime. So start with the original and then go to the left counterclockwise. Because this was just how it was written originally, this is a rotation of 90 degrees. Next one here. Same size, same shape is your first question. Hopefully you can see that yes. There's one other thing that's special here is notice the U is pointing to the right on both of these, so they're also the same orientation. If they are the same shape, same size, and orientation, this is a translation. Okay, just like with our rotations, though, we were specific. We said rotation of 90 degrees, 180 degrees. We want to use specifically what kind of translation here. Again, we start with the original. So from D, we have to go to the left one, and then we have to go up 4. You can write it two different ways. I like the rule better. We take our X value, and we subtract 1 to go to the left. We take our Y value, and then we add 4 to go up 4. If we wanted to write it using the vector, you would have to say translated along the vector. And then we use those hard brackets, the arrow ones, -1, 4. So either of these works for me, your choice. All right, same size, same shape, same direction. That's what we're thinking about here. So here, same size, same shape, but the W points down here, the W points to the right here. That doesn't work for us. Okay, so it's not a translation. Because it's the same size, it can't be a dilation, and we're stuck between a reflection and a rotation again. So start with a point. I'll start with W here, and let's connect it through the origin. So from here to here, that forms a 90 degree. Let's check the next one. Q to Q prime, that's not a 90 degrees. As soon as that happens, we are not rotating here, as soon as they don't match. That means this has to be a reflection. Now, with the reflection, we want to think, where could we draw a line to split this picture in half so that when we fold it, the pictures will line right on top of each other? Okay? So our options, remember, are the x-axis, the y-axis, y equals x, or y equals -x. So I'm just going to walk you through those really quickly. Y equals x. If I split it right here and take this and fold it, it goes down here. That doesn't work. I guess I should start on my original instead of that one. Okay? Then the next one, y-axis, if I take this and fold it, it goes over here. That doesn't work. Then y equals x, remember, goes corner to corner here. Well, if I split this and I fold it over, it would go right down here, which is not way up yonder. So that doesn't work. The only other option is y equals -x. And if I take this point and fold it over, it goes right onto that one. So y equals -x. So reflection over y equals -x here. All right, number 10 here, we want to think same size, same shape, same direction. So here, hopefully, immediately you can tell that these ones are not the same size. And as soon as you tell that, it's a dilation. Okay, we don't have to work hard to think about these ones in terms of what they are, but we do have to work a little hard to figure out what they're a dilation by. Okay, so the first idea here is, are we starting with the bigger one or the smaller one? Okay, so our regular DLW is bigger, so this is specifically a reduction. We're making it smaller. And if you noticed, when we were talking about an R value to make it smaller, that 1/2, it was less than 1. But then when we were enlarging something, the R value was greater than 1. Okay, so in general here, reduction, R is going to be less than 1, and an enlargement, or a stretch, it'll be greater than 1. Okay, so that's kind of a way to see if your shape looks right based on your scale factor, or your scale factor looks right based on your shape here. So what we're going to do is just look at some ordered pairs here. What I want you to do is let's focus on D. Let's write that ordered pair. It went from 0, 2, to the second one went to 0, 1. And we want to see what happened from here to here. Well, 0 to 0, we can't tell what happened because it didn't change. But from 2 to 1, we want to know what happened by multiplying, because our scale factor, we always multiplied. You can find that by saying 2x equals 1, just like we did with our first couple problems. Well, you'll notice if we divide by 2, x is 1/2. So when we take 2 times 1/2, or take half of 2, that's 1. Now, in general, this should work for all these points. I just want you to test it for at least one more to make sure you did your math right. Okay, so for L, let's look at that ordered pair. 1 to the right, 1, 2, 3, 4, 5 up. And then over here, L prime was kind of on this halfway point, so 0.5. And then it went up 1, 2, and it looks like a half. So then, if I take 1 times 1/2, I do get 0.5, so that works. If I take 5 times 1/2, I do get 2.5, so that one works, so that checks. So dilation with R equals 1/2. All right, last one here, also a dilation. Hopefully that's an immediate reaction because they're not the same size. And when they're not the same size, the only one that works is dilation. Okay, so again, focus on a couple points. I'll start at P, was negative 1, 1. And it went to P prime on the graph here was negative 2, 2. All right, our original here is smaller, so this is an enlargement. We should expect our R value to be greater than 1. Okay, so we're thinking negative 1 times what? Okay, you can use X or you can literally use R if you want. Let's go ahead and do that. Equals negative 2. Divide by negative 1. So R equals 2. Let's test it. If we times negative 1 times 2, we get negative 2. That's okay. If I take 1 times 2, I get 2, and that works. Again, I want you to check it with another ordered pair on the picture. Okay, so let's just look at M. M was positive 2, negative 2. And it went to, our M prime was 1, 2, 3, 4, negative 1, 2, 3, 4. So we're saying if we take this times 2, we should get this one. 2 times 2 is 4, that works. Negative 2 times 2 is negative 4, so that checks out. So it's a dilation with our scale factor being 2. All right. Hopefully we're going to get to a point where we can recognize these. Again, that's why we've been focusing on highlighting our shapes so we can see the pattern that's happening in the picture. Okay, but if you struggled with this, please come see me. And of course, always come in if you have any questions on your homework.